Okay, let's go ahead and take a moment to summarize what we've done so far. So let's summarize. What we've done is the following. First, what we did is we established that diagonalizability is too strong a condition, right? Not every matrix is diagonalizable, so that's not going to work for establishing a kind of general theory, okay? What we did next is we suggested block diagonals, okay? And we kind of confirmed that block diagonal matrices had nice properties under exponentiation. Now, where we finished up is we said Jordan blocks are nice block structures. Okay, so we established that Jordan blocks have this very nice form under exponentiation given by this binomial formula. Okay? All right, so let's go ahead and put all these different things together. And to do this, we're going to define something called the Jordan canonical form. All right, so definition, Jordan canonical form. All right, so this is sometimes abbreviated as JCF. All right, I'll write that as I go along. All right, so we say a matrix A in Cn by n is in Jordan canonical form, or JCF, if there exist Jordan blocks Ji in C ni by ni, where I goes from 1 up until p, such that J equals the block diagonal matrix of J1 through Jp. Okay? So a matrix is in Jordan canonical form if it's a block diagonal matrix where each block has the structure of a Jordan block. All right? Let me just write that out to make sure we all know what I'm talking about here. So I have J equals block diagonal matrix, J1 through Jp, where each Ji then has the structure of lambda i's down the diagonal, and then 1s just above the diagonal, right? And 0s elsewhere where, I haven't drawn anything. Okay, fantastic. So what this does is this puts together these two nice structures that we've kind of established so far, right? Jordan blocks, which behave nicely under exponentiation, and block diagonals, which do the same. Okay, so my question is then, can we transform any matrix A in Cn by n into a Jordan canonical form? So the answer, kind of nice, is yes, but with some caveats. Okay, so what we'll find is that we can actually always construct a complex transformation of a matrix into its Jordan canonical form, but this process is actually very numerically unstable, okay? So I want to emphasize the Jordan canonical form is a really nice theoretical tool, but in terms of practical computation, it's extremely limited, okay? So I'll illustrate a little bit later kind of these different issues in computation that arise. Okay, fantastic. So how are we actually going to go about constructing this transformation? So how do we construct this transformation? And in order to answer this question, I'd like you to kind of think back to your first linear algebra class where you were talking about diagonalization of a matrix, and kind of think about how you constructed a transformation that diagonalized a matrix. All right, so think about that for a moment. So let's think about diagonalization. Okay, so I'll assume you kind of gave that some thought. And you might remember that what you did is for a matrix A in Cn by n or Rn by n or whatnot, you would find a basis of eigenvectors. Right, which I'll denote as V1 through Vn, okay? And once you had this basis of eigenvectors, what you would do is you would take your transformation to be the transformation where the columns are these different eigenvectors, okay? And then you could compute T inverse AT, and this would be your diagonal matrix, okay? So first find eigenvectors, then compute transformation, then perform this product T inverse AT. What you get is your diagonal matrix. But the general problem, right, is if you have a non-diagonalizable matrix, you won't have enough eigenvectors, right? At a certain point, you'll run out of linearly independent eigenvectors and you won't be able to construct this transformation, right? That's what makes a matrix non-diagonalizable. Okay, so here's a basic idea, right? If we want to construct a transformation into Jordan form, right, which is really pretty close to being a diagonal matrix, we should look for a generalization of eigenvectors. Okay, so remember, our goal is to construct a transformation into a form that looks almost like a diagonal matrix. So to get a generalization of a diagonal matrix, we should look for a generalization of an eigenvector. Okay, that way we'll actually be able to find enough eigenvectors to form, or excuse me, enough generalized eigenvectors to form a basis for our space. Okay, so how are we going to generalize this idea of an eigenvector? Well, let's say, V is an eigenvector of some matrix A with an eigenvalue lambda, right? We know that means AV equals lambda V, right? And this is equivalent to writing A minus lambda I times V equals 0, right? That's an equivalent definition of an eigenvector. So what we can do is an easy way to generalize is to request that instead of just A minus lambda I times V equals 0, we'll request A minus lambda I to the K equals to the K times V equals 0 for some K greater than 0, right, where K is an integer. So now instead of just asking A minus lambda I V equals 0, we ask some power of A minus lambda I times V equals 0, okay? And this leads us to the definition of a generalized eigenvector. Okay, so definition, which is generalized eigenspace slash eigenvector. What I'll say is consider a matrix A, which belongs to Cn by n, with an eigenvalue lambda, which belongs to C. Okay? Then the generalized eigenspace of A with respect to lambda is the space K lambda of A, defined as the set of all vectors V and Cn, such that this condition up here holds, right? A minus lambda I to the K times V equals 0 for some K, right? So what I'll require is A minus lambda I to the K times V equals 0 for some K. So I just want to clarify, K is any number, any integer that's greater than 0, all right? It doesn't have to be the same for, every single vector in this generalized eigenspace. It's just some number for each vector. Okay, so that defines a generalized eigenspace. Now we define generalized eigenvectors to be elements of this space, right? So generalized eigenvectors with respect to lambda are just elements of K lambda of A. Okay, so this gives us a nice generalization of the idea of an eigenvector, which, maybe we'll be able to use to kind of compute this transformation into an almost diagonal form. Okay, so let me just establish some very, very basic ground rules about these spaces before we move on. So proposition, which is basic properties of your space K lambda. So I'll say that your generalized eigenspace K lambda of A satisfies the following two properties. So first, it contains an eigenvector, right? So K lambda of A contains at least one true eigenvector, right? Not generalized eigenvector, A. And, we see that this is true simply because, a minus lambda I to the first times v equals 0 means that v is going to be an actual eigenvector. Okay, so each of these spaces contains one true eigenvector, and then second, we have that this space forms a subspace. All right, so k lambda of A is a subspace of Cn. Okay, and this second condition, subspace, is just something that we kind of like to confirm in linear algebra whenever we take a subset of another space, right? If you have a subset in linear algebra, you should really want it to be a subspace to make sure you'll be able to do all of these nice linear algebraic operations. Okay? So the proof of this, this is going to be an optional problem on your homework. Okay, so you can give it a try there if you're interested. All right, so now what we've done is we've kind of laid out a definition of a generalized eigenspace, a generalized eigenvector, and we've discussed some very, very basic properties of these spaces. So the basic idea is these vectors form a pool from which we'll construct our transformation into Jordan form. Okay? So using these generalized eigenvectors, we'll go through a process very similar to the case of diagonalization to construct a transformation into Jordan form. Okay? So what we want to find now is some sort of special distinguished subset of these generalized eigenspaces that produces the right transformation into Jordan form. So in order to see what this subset of vectors should be, let's kind of examine some necessary conditions on these different transformations into Jordan form. All right, maybe this will give us some insight into the problem. Okay, so let's give this a try. So let's say let J equal T inverse AT be in Jordan canonical form. All right, let's just kind of manipulate this object to see what the different vectors contained in this transformation T need to satisfy. First, what I'll do is I'll just bring this T inverse to the right-hand side, right? So we require T times J equals A times T. Now I'll go ahead and expand this, right? So I'll have a block of vectors contained in T associated to each Jordan block, right? So Vj1 is my first block of vectors. Those are associated to the first Jordan block. Vjp, let's call it. That's where we finish up. And J is a block diagonal matrix, right? J1 through Jp. And this is equal to A times Vj1 through Vjp. Okay? So all that I'm doing is I'm just rewriting T in this block form, right? Where each block of vectors corresponds to one Jordan block, right? So these are the vectors associated with the first Jordan block. These are the vectors associated with the pth Jordan block. Okay, this just gives us a nice way of breaking up the problem. Now what we'll do is we will zoom in on one of these blocks. Okay, so let's try zooming in on the Vj1 block. All right, let's see what's contained in there. So let's go ahead and expand this product Vj1 times J1. And, this setup kind of tells us this product needs to equal A times Vj1, right? Let's go ahead and expand this. So what I have is Vj1 times J1 equals A times Vj1. Now I'll go ahead and I'll look inside this block, Vj1, and I'll see what vectors are contained in there. Okay, so what I have is Vj1 first vector all the way through Vj1, let's call it, the mpth vector, okay? This is going to be multiplied by lambda 1 through lambda 1 times 1, 1, right? Because that's the structure of a Jordan block. Okay, and then this is equal to my A matrix times Vj1, 1, all the way through Vj1 MP. Okay, so now I want to emphasize these quantities over here are the same thing, right? I'm just taking this vector Vj1, or excuse me, I'm taking this matrix Vj1, and I'm just looking at all the vectors inside. Okay? So what conditions do the vectors need to satisfy? Let's start by looking at the first vector, right? Here's what I'll do. let's take the product of this with this matrix over here. What that essentially amounts to is just taking lambda 1 times the first column, right? Let's equate that to A times the first column over here. So what we'll find is that lambda 1 times vj11 is equal to A times vj11, okay? And what this tells us is that the first vector is a true eigenvector. Okay, so it's not just a generalized eigenvector, but it's an actual legitimate eigenvector. All right, so let's try the second vector. Okay, so now what we'll have, let me just fill this out over here. We'll have a vj1, 2, so on. The second vector will take both the first vector, right, and the second vector. Okay, so let's see what this needs to equal to. So just by matching columns, once again, what we're going to find over here is that this second vector needs to satisfy vj11 plus lambda 1 times vj12 is equal to A times vj12. So let's solve for vj12. We'll just collect all those terms on one side. What we'll find is that vj11 is equal to A minus lambda 1I times vj12, okay? So what we find is that the second vector must satisfy a recurrence, okay? So the first vector is an actual eigenvector. The second vector needs to satisfy the special recurrence between vj11 and vj12 over here, okay? So this pattern actually continues. Pattern of the recurrence continues, right? And this is something you could prove or just observe just by seeing, okay, you know, we have this same kind of structure as we keep going along our columns, right? We go ahead and, you know, we kind of abstract away these required conditions in something called a Jordan chain, okay? So what we do is we take a look at this pattern, right, where we have, you know, these vectors satisfying this recurrence, and we say, this seems to be pretty important to a Jordan form, right? This is something that these vectors in this transformation need to satisfy, so I'm going to define it as something that's, you know, kind of fundamental to a Jordan form. Okay, so I'll say definition. This is called a chain of generalized eigenvectors. All right, sometimes this is also called a Jordan chain. Okay, so let's say let A in Cn by n be a matrix with eigenvalue lambda in C. So we say that a sequence, which is called Vi from I equals 1 up to m, is called a Jordan chain, or a chain of generalized eigenvectors with respect to lambda if the following properties are satisfied. So first, what we require is linear independence, okay? So this collection, Vi, I equals 1 to m, must be linearly independent, okay? Secondly, what we require is that this collection satisfies the recurrence that we defined above, right? So what this means is that the first element of this chain needs to be an actual eigenvector, and the other ones need to satisfy this recurrent pattern, okay? So first I'll write out the eigenvector condition. So A minus lambda I times V1 equals 0, right? It's the first one as an eigenvector. And then we require that A minus lambda I times Vi equals Vi minus 1. And this is for all I greater than 1, okay? So we have these two conditions, linear independence and recurrence. Remember, all that we're doing here is we're taking this pattern of recurrence, which we noticed vectors which construct the Jordan transformation need to satisfy, and we just abstracted those ideas away into this concept of a chain, okay? So chains are something that naturally appear in this transformation to a Jordan form. Okay, so that's what a chain is. And we have one special condition, right? So a chain is called maximal if it cannot be extended. Okay, so if I add another vector to it satisfying the recurrence, then that would need to give linear dependence of that set. Okay, so a maximal chain is one that we cannot extend while still satisfying these two conditions that we've given right here. Okay, so just real quick, I want to highlight, this is called chain of generalized eigenvectors, right? But so far in this definition, we haven't actually specified that these VI actually need to be generalized eigenvectors. The reason that we haven't made that specification is that this recurrence condition actually enforces that the VI be generalized eigenvectors, okay? So it's something that's automatically true, right? So this is a nice property to check. So check, chains are composed of generalized eigenvectors. All right. So here's what we've done, right? We took a look at this transformation into Jordan form, right? We examined individual blocks, and what we found is that we got this recurrence condition kind of arising naturally. Now we gave this recurrence condition the name of a chain, okay? And we found that these chains are composed of generalized eigenvectors. So finally, if we go ahead and we put all of these different things together, we can state a theorem about a transformation into Jordan form. All right, let me go and do that right now. So theorem, which is what we've been working towards all lecture, transformation into Jordan canonical form. So what I'll say is let A belong to Cn by n, and suppose A has k linearly independent eigenvectors, right? And these are true eigenvectors, right? V1 through Vk in Cn. Remember, k will not always equal n, right? For a general matrix, k will be less than or equal to n, because not every matrix is diagonalizable, right? Okay, so suppose A has k linearly independent eigenvectors, and let Vj I from I equals 1 up until Mj be the maximal chain starting at Vj, okay? So for each of these linearly independent eigenvectors, I'm going to go ahead and I'm going to compute the maximal chain which starts that eigenvector, okay? Then what I'll have is that beta, which is equal to V1I from I equals 1, oops, that should be an I. Oh, no, that should be a J. Up to M1 union all the way up until VKI, I equals 1 up to NK, forms a basis for Cn, okay? So if we do this construction where we take all of our linearly independent eigenvectors of our matrix and we compute all of their maximal chains, we put all them together, we actually get a basis for Cn, okay? So this is a really strong property. All right, now also what we have is for the matrix T, which just consists of V11 all the way through Vk sub mk, right, where we just take all of the elements of this basis and without changing their order, we put them into the columns of a matrix. What we have is that the matrix J equals T inverse AT is in Jordan canonical form. Okay, so let's summarize. What we have is we have a matrix A, we have its collection of linearly independent eigenvectors. We go ahead, we compute the maximal chain starting in each of those eigenvectors, and we put all of these chain vectors together into a big transformation matrix. If we compute T inverse AT for that transformation matrix, the result will be the Jordan canonical form of A, okay? So this is a pretty complicated theorem, all right? There's really quite a lot going on here. And it turns out the proof of this theorem is really quite hard, all right? So I provided a full proof of the theorem in the notes. It takes a couple of pages to go through, but for the sake of time, we won't cover it in lecture. Okay, very cool. So we've gone ahead and we've shown that, for any matrix out there, we can actually compute the Jordan form, all right? So I just want to highlight the Jordan form is not a silver bullet, right? Based off of this theorem, it might seem like we could kind of solve any problem we want with the Jordan form, but there's a lot of computational issues that arise with it, okay? So Jordan form is fragile, okay? To say exactly what I mean by this, let's take a Jordan form that looks like this, right? So this is a Jordan block, right? Now if I take any arbitrarily small parameter, so let me call it epsilon greater than 0, then I perturb this matrix so that I get 1, 1, 0, 1 plus epsilon, this is no longer a Jordan form, right? Because for epsilon greater than 0, 1 and 1 plus epsilon are not equal, right? So there's no way this can be a Jordan block, okay? So the problem is, with an arbitrarily small perturbation, we've disrupted the Jordan form, okay? So this example kind of highlights that the Jordan form, although it's a really nice tool for theoretical computations, is something that's really quite fragile in practice, right? And this is something you should always keep in mind if you're doing, say, numerical computations. Okay, so with this said, I finally want to return to our original motivation, which is computing exp of a, all right? So we've finally gone through and established that we can, in fact, compute this Jordan form for any matrix. Now what I want to convince you of is that we could use it to compute the matrix exponential, okay? What I'm going to show you is how to compute the matrix exponential of a single Jordan block. Once you have that, it's just simply taking the exponentials of each block in your block diagonal structure and sticking them all together, okay? So what I'm going to say is proposition computing the exponential of a Jordan block. What you have is let j equal lambda I plus n naught be a Jordan block. Okay? Then the exponential is computed. Exp of jt equals e to the lambda t times 1, 1, t, and this pattern of increasing powers of t kind of repeats all the way until the edge where we get t to the n minus 1 over n minus 1 factorial, where n is the size of this matrix, okay? Okay, so how are we going to derive this formula? Well, what we're going to use is a couple of really nice facts about, this matrix n naught and this matrix lambda times I, okay? So the proof, I'll take advantage of this fact, which you will also prove on your homework, that if a times b equals b times a, then the exponential exp a plus b is equal to exp a times xb, okay? So for the case of lambda times I and n naught, is it the case that a times b equals b times a? Well, certainly, right? So we know lambda I times n naught equals n naught times lambda I, right? This is just a property of the identity matrix, okay? And from this, what we can conclude is that the exponential of j times t, right, which equals the exponential of lambda I times t plus n naught times t, is actually equal to the product of these two exponentials, right? Exponential of lambda I times t multiplied by the exponential of n naught times t. Now the exponential of lambda I times t is easy to compute, right? This is a diagonal matrix. We could show that this guy is just equal to e to the lambda t times exp of n naught times t, okay? So all we need to do now is compute the exponential of n naught. But remember, earlier what we had said is that n naught to the n equals 0. So all that we need to compute is the first n minus 1 terms of the matrix exponential. Okay? So as a consequence of this property, what you'll find is that exp of n naught times t is equal to the identity plus n naught t plus n naught squared t squared over 2 factorial plus n naught to the n minus 1, t to the n minus 1 over n minus 1 factorial. Okay? So what you'll have is that your exponential of your Jordan block, jt, is equal to e to the lambda t times this formula up here. Okay? Now, using that shift to the right rule that we established earlier for computing the powers of n naught, you should immediately be able to see where these diagonal rows kind of come from. Okay? So for each term, we simply take a power of t, we shift it up one along the diagonal, and we keep going all the way until we get to n minus 1. All right? And that's where this formula comes from. All right? That's a proof. Thanks for watching.